Hi guys, subscribe our channel Science World and hit that bell button so that whenever we upload a video, you get the notification. Today's topic is Maxwell's thermodynamical relation. From the two laws of thermodynamics, Maxwell derived 6 fundamental thermodynamical relations, which are known as Maxwell's thermodynamical relation. Now, from first law of thermodynamics. From first law of thermodynamics, what we get? We get dq, that is equal to du plus dw. Now here q is represented as the heat and u is the initial energy of the body and w is the work done. Now we can modify this equation and we can write du is equal to dq minus dw. Also again we can write du is equal to dq minus pdv. We can give this equation as number 1. Now here dw is written as pdv because we know that work done is equal to pressure multiplied by volume. So here dw is equal to pdv. Now again from second law of thermodynamics, we get ds, that is equal to del q by t. Now here ds is equal to del q by t, where s is the surface area and we can say q is the energy and t is for time. Now we can modify this and write del q is equal to t ds. Now let's put it equation 2. Now putting equation 2 in equation 1, we get our equation 1 was du is equal to dq minus pdv. So in place of dq we use this partial differentiative of q, that is tds. Hence we get du is equal to tds minus pdv, and we give the name of this equation as number 3. Now let us consider u, s and v are the function of two independent variables of x and y. So when we consider u, s and v as the functions of two independent variables of x and y, we can hence write du is equal to partial differentiative del u by del x keeping y constant into dx plus del u by del y keeping x constant dy. Again in the same way we can write ds is equal to del s by del x keeping y constant and multiplied by dx. Also del s by del y keeping x constant and multiplied by dy. And in the similar way for dv also we can write del v by del x keeping y constant multiplied by dx plus del vy del y keeping x constant into dy. Now these values du, ds and dw, we substitute it in equation 3. Now substituting these values in equation 3 we get. Now substituting these values in equation 3 we get, now putting the value of du here, we get del u by del x keeping y constant dx plus del u by del y keeping x constant dy, that is equal to t third bracket del s by del x keeping y constant dx plus del s by del y keeping x constant dy, and then closing the bracket. Now for the second part we have, for minus pdv we write minus p third bracket start del v by del x keeping y constant dx plus del v by del y keeping x constant dy. Again, now we can modify this equation. Now we can substitute by separating dx and dy. Now here we separated t del s by del x y minus p del v by del s x whole bracket dx plus t del s by del y x minus p del v by del y x whole bracket dy. Now comparing dx and dy we get. Now here what is done, this equation we get from here, so we compare the dx. In this portion the coefficient of dx is del u by del x keeping y constant, and coefficient of dy is del u by del y keeping x constant. So we take the coefficients and compare it, and then we get del u by del x keeping x constant is equal to t del s by del x keeping y constant minus p del v by del x keeping y constant. We give this equation 4. Now also we get from the second dy, comparing dy we get du by del u by del y keeping x constant is equal to t del s by del y keeping x constant minus p del v by del y keeping x constant. We put this equation number 5. Now differentiating the equation 4 with y and the equation 5 with x, we get. Now for equation 4 we differentiate it with y, so we get del square u by del y del x is equal to del t by del y keeping x constant del s by del x keeping y constant plus t del square s by del y del x minus, now we can put this in a whole bracket, minus del p by del y keeping x constant del v by del x keeping y constant minus p del square v by del y del x. Now what we did here is a simple formula of derivative, taking the first one's derivative and keeping the second term constant, and in the second time taking the second's derivative and keeping the first constant. So what we did here is taking the derivative of t first and keeping ds by del s by del x a constant. Now in the second term what we did is just taking the del s by del x derivative and keeping the t constant. So this is the formula and we brought the result here for the first equation 4. Now say we give a name here as equation 6. Now for equation 5 we get del square u by del x dot del y is equal to del t by del x keeping y constant, del s by del y keeping x constant, plus t del square s by del x into del y. Now we can put it in bracket. Also again for the second term we get here del p by del x keeping y constant, del v by del y keeping x constant, minus p del square v by del x into del y. So we can put it as equation 7. Now we know that the change in internal energy is brought by the change in the volume v and the time t. Now whether v is changed to del v or dv and t is changed to dt or del t, or the vice versa, let it the t change first and then the v change first. So in that case we get that du, this du, it is a perfect differential. So the change in internal energy is brought by changing v and t, whether v is changed by dv first and t by dt, or we say vice versa. So in that case we get du is a perfect differential. So if du is a perfect differential, then we know that del square u by del x into del y is equal to del square u by del y into del x, since it is a perfect differential. Now here, as we got del square u by del x into del y is equal to del square u by del y into del x. So from equation 6 and equation 7 we saw that left hand side we got equal, hence we can say that right hand side is also equal. So from this we can write, that implies del t by del y keeping x constant, del s by del x keeping y constant, plus t del square s by del y into del x, minus del p by del y keeping x constant, del v by del x keeping y constant, minus p del square v by del y into del x is equal to del t by del x keeping y constant, del s by del y keeping x constant plus t del square s by del x into del y minus del p by del x keeping y constant del v by del y keeping x constant minus p del square v by del x into del y. So from this equation 6 and 7 we got that both the equations right hand side we got it equal. Now next step what we get is that since ds and dv are also perfect differential, since ds and dv are also perfect differential, so we have del square s by del x into del y is equal to del square s by del y into del s, and also del v by del x into del y is equal to del v by del y into del x. Now in this equation we give it as equation number 8. In this equation we see that del square s by del x del y is equal to del square s by del y del x, so we can cancel this term and this term, and also del v by del x del y is equal to del v by del y del x, so we can, it is del square v, so we can cancel this term with this term. So after all the cancellations the equation 8 reduces to del t by del y keeping x constant, del s by del x keeping y constant minus del p by del y keeping x constant, del v by del x keeping y constant is equal to del t by del x keeping y constant, del s by del y keeping x constant minus del p by del x keeping y constant, del v by del y keeping x constant, and also this is the general expression for Maxwell's thermodynamical relation relations. So this is the general expression for the Maxwell's thermodynamical relations. Now also we'll find out what are the 6 thermodynamic. Now for our convenience we wrote the Maxwell's general equation here. Now from this equation we will find out the Maxwell's 6 relations. Now for first relation we put some condition. Now what are the conditions? Now we put x is equal to s and y is equal to v in above equation, in this equation. So from here we get del s by del x is equal to 1 and also del v by del y is equal to 1 as x is turned into s and y is turned into v, and del s by del x, del s by del s is equal to 1, del v by del v is equal to 1, and also we get del s by del y is equal to 0 and del v by del x is equal to 0. Now since y is turned to v, so del s by del v turns 0, and x is turned to s, so del v by del s turns to 0. Now from this equation, now if we cancel the terms and put 1 in place of the terms, we get the final equation. Now substituting in the above equation, we get del. Now here what happens, del s by del x, it turns into 1, so we get del t by del y term. So del t by del y x. Now here del v by del x turns to 0, so this term gets cancelled. Now behind the equal, what we get, del s by del y turns to 0, so this term gets cancelled, and del v by del y turns to 1, so we get on the right hand side of the equal sign minus of del p by del x, keeping y constant. But now del y will turn as del v, and del s will turn as, del x will turn as del x. So this equation again turns into del t by del v, keeping x constant, or in the place of x we write the value we choose, x is equal to s. So in the place of x we write as s is equal to minus of del p by del s, keeping v constant. So this is Maxwell's first relation. Now in the same way, for second relation, we put, let x is equal to t and y is equal to v. So from here we get del t by del x is equal to 1, del v by del y is equal to 1, del t by del y is equal to 0, and also del v by del x is equal to 0. Now again putting these values in this equation, we will find del s by del v, keeping t constant, is equal to del p by del t, keeping v constant. This is second relation. Now for third relation, we put x is equal to s and y is equal to p. Now when we put x is equal to s, we get del s by del x is equal to 1, and del p by del y is equal to 1, and then del s by del y is equal to 0, and del p by del x is equal to 0. Now again putting these values in the above equation, we will get del t by del p, keeping s constant, is equal to del v by del s, keeping p constant. Now this is third relation. Now for fourth relation, we put x is equal to t and y is equal to p. Then we get del t by del x is equal to 1 and del p by del y is equal to 1. Also we get del t by del y is equal to 0 and del p by del x is equal to 0. Now putting this, we get del s by del p, keeping t constant, is equal to minus of del V by del T keeping P constant. This is fourth relation or fourth Maxwell's relation. Now fifth relation. Now for fifth relation we put x is equal to P and y is equal to V. So we get del P by del x is equal to 1, del V by del y is equal to 1, del P by del y is equal to 0, and del V by del x is equal to 0. Now substituting these values, we will get a relation something like this: del T by del P keeping V constant, del S by del V keeping P constant, minus of del T by del V keeping P constant, del S by del P keeping V constant is equal to 1. We will get the fifth relation like this. This is fifth relation. Now for sixth relation. Now for sixth relation we put x is equal to T and y is equal to S. Then we get del T by del x is equal to 1, del S by del y is equal to 1, del T by del y is equal to 0, and del S by del x is equal to 0. So for this we get a relation like this: del P by del T keeping S constant multiplied by del V by del S keeping T constant, minus del P by del S keeping T constant, del V by del T keeping S constant is equal to 1. This is sixth relation. So these are the Maxwell's sixth relation which Maxwell derived from that Maxwell's thermodynamical relation.